sir.
Okay, thank you.
So, good afternoon to one and all, and I welcome our foreign experts, Professor Hamid Raza Karimi sir, on day 5 of this one-week GAN course on resilient control of cyber-physical system. So, welcome you, sir, and in this sessions, in the first half, we will have a 2 hours lectures. Sir is going to deliver his lecture on this model predictive control and its deployment to this cyber physical system framework. And then we have 1 hour tutorial sessions. And as I requested you, sir, that at 15:55 India Standard Time, we will have a short interactions with the participants. So, and 4:15 we will again continue the tutorial sessions. So now I hand over the sessions to our foreign experts. Sir, the session is, it can be started, sir.
Okay, thank you very much, Dr. Dipayan Buhato, for introducing the topic for today. So, good afternoon, everyone. So, as Dr. Buha, he mentioned that today we start with the topic of MPC. So, for the MPC as a model predictive control, so basically we should know that what is the MPC, in fact, from the state of the art. So if you look at some application like the mobile robot or the autonomous cars, so usually the system should work in some environment, and the environment could be the complex, or should the environment could be the unknown, and that's it. So we need to remember that how we can look at our prediction for the next step. It means that how the system should take action for the next time. So this kind of the forecasting or the prediction is a challenging topic. So first, we need to think about how to design the control. So in terms of the control design, so you need to think that there is several constraints in your modeling. So the constraint could be from the environment, from the geometry, and all should be basically, they should be updated. So this kind of the time varying the obstacles or time varying constraint, and then they bring some difficulties to the solving the problem. So if you want to solve the kind of the model predictive control, so we need to remember that this is a sort of optimization problem. So at each time, you need to optimize the one cost function. So by doing this kind of the optimization part, so in the maybe the sequentially, so you should be able to calculate the next control actions. So the point is that should we do some which kind of optimization techniques we should use it in our case. So some optimization techniques are static. So or some optimization is the dynamic, and this means that we are moving to the dynamic optimization. So this brings another issues in the optimal control. So now you know that in optimal control, we are familiar. We are trying to optimize one cost function. So typically what we learn in other courses, the optimization is a sort of a static. So you try to optimize the basic control signal, so without consideration other effects, such as the constraint or some sort of the prediction aspect. So the family or the context of MPC was produced based on the receiving horizon control. It means that if you have a short time horizon or the long time horizon, or what could be your the receiving horizon, and you should consider it in the control action. So now you can see that the model predictive control is based on the mathematical model. So now what you are doing, you should have a mathematical model. It means the N means the mathematical model. So this mathematical model should be predicted because the model is changing. And that's it. The sort of prediction could be also the issues should be considered. Okay, so now MPC becomes very important in many applications. So for instance, the MPC, so it leverages the constraint static optimization for optimal control problems. So if you look at for example, the CPS or even the network control systems, so you have a plant, then you have some output data, you have a measurement, so you have an input signal. So now the point is that based on one reference signal, it means that what should we do actually? Basically, we want to do some tracking, for example. So now this kind of the control, it consists of the issue, some information of the model, information of the constraint, and also our objectives. So this optimizer is a plan. So not the plan means that how much you want to make a plan over the time. So if you want to do the long-term plan or if you want to do the shorter plan. So in fact, MPC is the real time, is a sequential optimization with the constraint on both information. We have the input signal and also the state of the plan. So all could have a constraint, and this is a very important part. So in other courses, when you talk about the LQR, for example, the linear quadratic control, so you also minimize the cost function. But in LQR, you didn't have any constraint on the state or the input, and that's it. So these issues in the static optimizations, so with the sort of the constraint. So this brings us to the context of the MPC. So the MPC applications is including the horizon, time horizons. So you can see that if you look at the computer control, the horizon time is the scale of the nanoseconds. So in the traction control for example, for the cars, so in the milliseconds. So in the refineries, in the minutes. So train scheduling in the days. You see, so different applications, so they have a different time horizons. This depends on the applications. So if you work on the wind turbine and the power system and the microseconds, so if you do some prediction on the buildings and the seconds, for example, on the health, for example, the hours and also in the production plan is a weeks. So this it tells us that depending on the application we have, but basically this time horizon should be considered properly. It depends on the application task. So in this module, we can see that the simple, basically the control optimization control problem can be very hard to analyze and solve. So you see that even if we have this optimization problem with the constraint is not easy task. So that's it. The OCP, this becomes harder if you have a constraint on the state and control. So as I told you that if you have a constraint, so on the state and control, so basically the problem becomes much difficult. So basically to solve. Okay. So another thing is that the most physical system have a constraint. So whatever you do in engineering, you always deal with the constraint. So sometimes you have a constraint on the safety limits about the min and max capacities for some sort of the component in your application. So you could have an actuator limitation, avoiding the saturation, the overshoot constraint in the response of the system. So now you can see that in practical system, we already deal with this kind of the uncertainty or the constraint. So now the MPC, the model predictive control, provides a great alternative to solving constraint optimization control problem in comparison to HJB. The HJB is a Hamiltonian-Jacobi Bellman, and this is also another optimization problem. So now you can see that the MPC, so it's another solution we have for solving the optimization problem mathematically by considering the constraint. And that's it, the MPC becomes practically very useful. Okay, so if you want to say more about MPC, so the MPC, it means that first you need to look at what is your time instant. In the current time instant, an MPC can be used. Then what information you have? Information you have is the current inputs, and also you have information about the current output and current state. So this information you already have at the time instant. So you need to use this information, and then you need to do some computation of MPC. But if you want to do the MPC computation, you should look at it over the some prediction horizon. The prediction horizon depends on the application you have, but this should be what would be the future, what is the next optimal control sequence. So if you remember that yesterday I talked about the self-triggering control for MPC. So the self-triggering control, so it also gives you some next control action should be updated. So when I'm saying the next time instant, it's a future time. Okay, so but sometimes we don't know what is this future time. So in MPC, the future depends on you. But you can fix what is the prediction horizon. But I can tell you that in control, if you want to do some event-based control, so specifically the self-triggering control, so then the prediction horizon so could be taken from one set, and then you need to use what is the optimal prediction horizon. So yesterday when I show you one example about the MPC, then I told you that the prediction horizon for the lecture yesterday, it was also selected from optimization part, and this was very interesting. So maybe you could, again, after the lecture today, you can come back to lecture yesterday and then to see more about this kind of the optimality of the prediction horizon. Okay, so what is the issue? The issue is that the next optimal control sequence should be calculated. So how to calculate? You need to solve in the online. It's a real time. But that's it. This should be done in the real time. But of course, it depends on the type of MPC. So if you have this explicit MPC or the eMPC, explicit MPC, so it's solved in the offline form. So that's it. We have two types of the MPC. We have an explicit MPC and we have an implicit MPC. But sometimes in the explicit MPC, so this calculation will be done in the offline form. But in fact, in the implicit MPC, IMPC, so the computation will be done in the online form. So let's look at the picture in the left side. So here you have the prediction horizon. You see that at the time ti, so you could have a one prediction horizon, two prediction horizon, up to NP. And then you can see that this is your data. You see the data y at the time instant ti. So here the control signal can be updated as a UTI. So now the control signal is fixed until the next time instant ti plus 1. At the ti plus 1, again, the control signal can be updated. So this updating depends on the horizon NP. And therefore, you need to find what should be the shape of the control signal like this. So usually in MPC, the control signal, it looks like a stair. You see, there is a stairs shape, but the important is what could be the time of the updating of the next control action. So if you bring it to the case of the MPC in the block diagram, so as we discussed before that you need to take the data. The data means the measure signal if you have a state, for example, the state at the time instant Ti. So you can bring it to the copy of the plan. So this is the MPC. So now the reason that we call it MPC because you need to give a copy. This could be a copy of the plan, okay? And then these model plans, so should they give us some prediction of the next output signal, and then you can take it to this set point, and then the prediction error can be calculated. So prediction error, it goes to the optimizer, and optimizer, you have a cost function, you have a constraint, and then you need to solve it. And then after doing the optimization, you can get the predicted input signal, and then you can apply. So this signal, you can see in the next time instant, so it can be calculated from this MPC block. Of course, the MPC depends on the model, but in reality, maybe we don't have a model, then that's it. Now there is a sort of a data-driven predictive control. If you are interested, maybe you can contact me to see more about the new research areas we have in the data-driven predictive control. Okay. So let's do some mathematics. So you notice that in the linear MPC, so what does it mean? The linear, we have a linear plant, and also it means that you have a cost function, you see J. So this cost function J depends on the state, depends on the control signal U, and depends on the parameter NP. This is the prediction horizon, okay? So what is the next? The next is you need to minimize it over the control action UT. So if you minimize the cost function respective of control action, but there are some constraints. So the constraint one is the dynamical system. This is a mathematical model. And there could be some constraint over the control signal, some constraint on the state, and based on that, you can basically find this sequential of the control action UT. So the control action UT can be calculated. So up to this based on the horizon NP. So in this case, so you can basically calculate this optimization problem. So at each time instant, so you need to measure or estimate XT. At each time instant, you need to measure and or estimate a state. You need to find the optimal input sequence and the prediction horizon NP. So it means that you need to find this optimal sequence UT star, because based on this optimal input sequence, so this would be the control signal is applied to the system. So if you want to implement it, you need to implement the first control action UT star. It means that when you are repeating this kind of calculation, so you can calculate this sequence, but first you can apply the UT star. You can calculate it from this optimization problem. So the linear discrete time MPC. So what is the objective? So the objective is to apply MPC for this linear time invariant discrete time system. So now you have a discrete time system. So with the A and B and the measure signal YK. So if you want to apply the MPC, first you need to look at what is your deviation of a state, delta X. So delta X is the xk plus 1 minus xk, and then you can get this A delta X plus B delta U. This is the definition for the change of state. So the change of the measure signal delta y is the yk plus 1 minus yk. And then you can calculate, if you put this mathematical formulation here, so you can get is a c delta xk plus 1. And this becomes this formulation, okay, ca delta x plus cb delta u. So now you have here delta y is this, delta x is this mathematical equation. So finally, you can see that the yk plus 1 is equal yk plus ca delta x plus cb delta u. You can get this equation from here. Okay, so now you can combine, because now you got this equation and this equation and the equation at the beginning, so you can combine it together. So when you combine it, so you can get this vector. So this vector is the delta xk plus 1, yk plus 1 is equal a0 cait delta xy plus bcb delta u. Okay, so this is again the matrix form. You can get this as an augmented state. You can get as a xa, k plus 1 as the augmented state. So you can get this matrix as a phi A and this matrix as a gamma A. So what about the yk? Because yk is here, y is a cx, okay? So from this formulation and also consideration xa is this, so yk becomes 0 ip, it becomes ca. So ca multiplied xak. So this combination, why this is important? Because this combination, it shows you what is the updating or the innovation basically of the X over the time. And at the same time, you can also consider information Y. And this is the reason that this equation can help us to calculate the next state in the prediction horizon. Okay, so now you got this mathematical model. So this mathematical model is xak plus 1, phi a xak plus gamma a delta uk. And you remember that the yk is the caxak. So now you need to assume that the control signal uk and state are available. And then it means that based on this assumption, you can calculate xk plus 1. So if you could calculate xk plus 1, consequently, xa is also given, because if you know xk plus 1, definitely you can also, also the xak, and this is also the given. So the control objective is that how to construct the control sequence. So the control sequence delta uk plus 1 up to the delta uk plus np minus 1, and the np is the prediction horizon. So the point is that how we can basically construct this the sequence of the control signal. But this sequence will give us the predicted state vectors. It means that if you know this sequence, so based on this sequence, so you can calculate the predicted state vectors, something like this. So for the xa, at the time k plus 1, for the information given at the time k, so this set of the state information, so it is a sort of the prediction state vectors. And based on this, you can also get what is the next measured data. It means that you can do the prediction over the measured data, what is the yk plus 1 for the given k. It means that for one horizon, prediction horizon in P, so you can get some prediction on for the next measured data, for the next state vectors. It means that you could have a good prediction for both a state and also the measurement. So now if you want to do the MPC construction, so the first thing is that how can we construct the control signal for a given xk? So if you want to design the control signal for a given xk, so this is looks like the least square problem, but it means that you need to do some optimization problem. So we can again come back to our mathematics. So we can write the predicted future state variable. So based on information for xak plus 1 given k, so this information has such a formulation. And again, if you repeat it for the next and the next and the next, the basically up to the prediction horizon NP, so you need to repeat this formulation in such a way. So for the time k plus 2, for the given k, so the formulation is like this: phi a xak plus 1 given k plus gamma a delta uk plus 1. So now you need to substitute xak plus 1 for given k. You need to put it here, and then you can get this equation, okay? So now this equation depends on xak, delta uk, and delta uk plus 1. So now if you repeat it and repeat it up to the k plus np, so you can get this mathematical equation. So this mathematical equation is the representation of the prediction horizon. So XA at the K plus NP. So based on XAK and delta U information. But here there are some for some matrices, and these matrices also be calculated. And therefore, the MPC has a bit very heavy in the computation task. So now you can write down. So this mathematical formulation can be represented in this form, okay? So you can write it in this form, CA. So multiply these vectors. So the vector you got it from here is the CA, multiply this column matrix of the phi A up to here. You can get this from this equation, multiply xak, and then there is one matrix like this, multiply the sequence of the control input signal from delta u up to the delta uk plus np minus 1. Okay, so this mathematical model, so is a sort of the predicted output signal can be calculated because the CA multiply y from here. So you can also calculate the y as the y transpose k plus 1 for given k. It means that all the information of the basically the future measurement, so based on the prediction horizon, so you can basically calculate it from these mathematical models, so from the WXAK, the plus Z delta U. So this formulation is interesting because on the left, you have a prediction for the measured data. It depends to the information of a state and also depends on the sequence of the future control. Future control, current state, future measured data. And this is a means that you got a very good relation between the local information and the future information. Okay, so this mathematical model, let's write it like this. The vector y, so it's become WXAK plus Z delta U. So the Y, W, Z, XA all are given. And then you need to determine delta U because what is the task? The task is what is the sequence of the control signal delta U. So this sequence, so you can calculate it from optimization. It means that you can calculate all of the sequence of the delta UK up to this. So assume that we want to minimize this cost function. So let's assume that you have a cost function J. So this depends on you. You can define the cost like this. It's a function the J on delta U. is the one quadratic function for the tracking because r minus y, you want to do some sort of the tracking. And then you have also one cost function for the energy optimization, and this is the energy of the delta U. And the Q and matrix R is the positive definite matrices. So this cost function is similar to the LQR in the control linear quadratic regulation problem. But you need to minimize this cost function. So from the output set point and also the control actions. So it means that we need to see how to minimize the cost function with respect to the control action. And this is a unconstrained optimization problem, but of course it's easy to solve. So this optimization problem is easy to solve. How to do it? So you need to calculate the round of j, respect to delta u equals 0. So if you apply this principle of the deviation equals zeros, you can get it from this mathematical equation, delta u star, it has such a formulation, okay? So this mathematical formulation, this is an optimal control action. So you can get it for this problem. But of course, one thing is interesting for you to see. So if you want to see that if this is exactly the minimum point or the optimized solution for this quadratic problem, you can calculate another derivative. If you calculate the second derivative of the j respect to u, then you will get this mathematical formulation, and it says that this is positive. So this means that this control signal, this solution is the optimal solution for this problem. Okay, at this point, you got the optimal solution for the control action delta U star, and this is basically the solution you have obtained. So now you need to move on to the next step. You need to compute delta UK. So in this case, if you want to calculate delta UK, so you remember that the delta UK respect to the delta U, it has such a formulation I 0, 0. If you multiply with delta U, you can get the delta UK. So delta U, you got from previous slide, if you got from this equation, so you can put it here, and then you can get delta UK. Okay, so this is your control basic sequence. So this delta UK, so can be written like this. So if you simplify this equation, you get the KRR minus the KRW XAK. Of course, the KR metric looks like this, okay? So now you got delta UK and relation with XAK and also the set point. You remember that we introduced XAK as the augmentation of the delta X and the YK, okay? So if you remember this augmentation state, so you can also put it here in this equation, and then you can also simplify it. So now you will see that the delta UK is a KRR minus KMPC delta X minus KY multiplied YK. Okay, so this term, because the KY multiplied YK is information, is your sensor data, you can add it to the KRR. You will get the KRR minus KYYK minus the KMPC multiplied delta XK. So this problem is a state feedback gain. You see, you remember that the delta UK is the delta X. Is exactly this is the state feedback control. And you got this kind of the state feedback gain. And what about this? So KRR minus KYYK, this is the reference signal. And that's it. You have a reference signal. And also here you have some state feedback control. And you remember that from this equation here, KR is this, and KMPC is this. So now, and also KY is this. So this formulation, it shows that you try to calculate what is the gain of the MPC. You can calculate from this formulation. So, okay, if you want to solve the unconstrained MPC problem, there is a one algorithm. Uh, so this problem I explained that there is no constraint on the MPC. So if you want to solve it, first you need to discretize your system. First you need to find your matrix A and B for the discrete model. So you need to specify the prediction horizon NP. And then you need to find augmented dynamics. You need to obtain XAK plus 1. You need to obtain phi A, gamma A, and CA. And then you need to compute the WZ and also the formulate predicted output equation like this. So these two matrices can be computed. And then you need to look at the reference signal and the weights on the control action. You need to give some parameter to the cost function J. It means that you need to build the cost function J. And from cost function J, we can compute the optimal control delta U. And then you need to find delta UK and UK. So these are the some steps. So for solving this unconstrained MPC. So I'll give you one example. So let's assume that for the linear MPC, so we have a matrix A and B after discretization and the vector C. And assume that you have this prediction horizon NP equal 10. Okay, for this prediction horizon 10, you can apply the algorithm. So as I told you before, first you need to calculate phi A, gamma A, and CA. Exactly as step number one. Step number one, you need to do some augmentation of the dynamics to obtain phi A, gamma A, CA. In the step number two, you need to calculate the metric Z and W. You can calculate this the metric Z. And this is a matrix, the W. And then you need to come to the other steps to calculate the delta U. You need to solve delta U from the cost function J. So then you need to apply the control and generate a state and dynamics. So here there are some plots. You see for the matrix R and for 0.1 I and the bigger R. It means that for a small r and a big R. So it means that putting more weight on the control action is reflected in the left figure. So this left figure, it means that if the R increase, so basically you get because you remember that the matrix R is a weight on the control action. And these are basically the plot of the control. So it means that by increasing the R, so basically you can also if the R increase, so the control action also decrease, and this means that you could get basically the less effort in the control plot. So now you can see that what is the effect of the R in the control response for the different parameter R, and then you can see the output. This is the output, and this is a control, and this is the output, and this is a control, and it means that if you increase the R, so the control effort basically decreasing, and for the small R, the control effort is a bit higher. And but a state more or less is the same. You see the state or the measured data is more or less the same. Only the amplitude of the control action is changing. So if you want to get the less control actions, so you need to increase basically the R. If the R increase, so the control action also decrease. Okay, so now we look at the MPC. We look at MPC with the constraint on the control action delta UK. So this is the same problem, but only one question. The question is that we have the constraint on the control signal delta UK. So we assume that the delta UK is bounded. It means delta UK is between the delta U mean and delta U max, okay? So for this kind of the assumption, so you can write down this you can find this formulation. So this formulation says that minus I multiplied delta UK is less than this. So this mathematical formulation is exactly this formulation. But why we need to write like this? Because we want to take it to our the vector matrix calculation in MPC. So now you need to look at the prediction horizon NP. So you remember that for this prediction horizon NP, so based on the sequence of the control action delta UK up to here, so if you multiply this and this, so you can get this one vector like this. So this vector, so minus delta U mean, delta U max, minus delta U mean, delta U max. It means that this mathematical formulation, so should be valid for all the control sequence of the delta U, because all the delta U is satisfy this condition. Okay, so this augmentation says that this new vector is a delta U. Okay, so now you have a matrix multiply the vector delta U is less than this vector you got it on the right side. So now what is the control? What if the control is a bounded? So in this case, how to solve the problem? So we know that basically the UK is the UK minus 1 plus delta U. And then you can see that the delta UK, you can write it like this, I00 multiply the vector delta UK. So now you have a relation between UK minus 1, delta UK. So if you repeat it, so you could also say that similarly, you could say that so this UK plus 1 is the UK plus delta UK plus 1. And if you repeat it, you get this mathematical formulation. And if you repeat and repeat and repeat up to UK plus NP minus 1, you can get this mathematical model. So this mathematical model is interesting because this vector is the UK. This is a matrix, all is identity, is a matrix E, multiply UK minus 1. So here you got another matrix, matrix H, and then it should be multiplied with the vector delta U. You see, you can get it here. So you can keep this equation, and then you remember that the UK should be between the mean and the max values because there is a constraint. So this also can, this constraint, it can be also represented like this. So this constraint is exactly the same, but why we should write like this? Because we want to take it to our mathematical calculation. Here we have a minus UK is less than this. So from this slide, here you have this equation, okay? This equation is this. And then you need to remember that from this equation, so minus H multiply delta UK. So in this case, it should be less than this term. So it means that if you combine these two equations, so you can find that this mathematical formulation is valid. So you can write it as from these two terms. Okay, so in this equation, you can see that this is an input constraint MPC because here now you have a constraint on the delta U because you remember that the delta U is a one parameter in the cost function J because J depends on delta U. So now if you want to minimize the cost function J with respect to delta U, you need to remember that there is another constraint like this. So this constraint, so basically we call it as a MPC with the control constraint, and this should be also solved. So another issue is about the MPC with the output constraint. So now you need to repeat it again. If the yk between the y min and the y max, okay? So now exactly the same process. You need to write like this: minus yk is less than this. But this time you need to back to yk. You remember that the yk, it was the omega xa plus z delta u. So if you combine these two equations, so you can obtain this equation. So you can obtain minus z delta u k is less than this. So this expression again, it also brings the constraint to your MPC, because when you want to minimize the cost function j respect to delta u, so now you see that this delta u should also satisfy this condition, and this condition depends on the y min and y max, because this is an MPC with the output constraint. So now I told you MPC with no constraint, MPC with the control constraint, MPC with the output constraint. Even you can add it again, MPC with the input and also output constraint. Again, the same process. You need to add more constraint to your optimization part. And this is a issue we have in MPC. So MPC becomes more difficult if you have more constraint, because more constraint means more computation. And also because MPC should be done in the real time. And that's it, in the real time. If the computation time is high, you cannot do it. And that's it. The big difficulties in MPC is about implementation, how to implement MPC in the real time. Okay, so now this is about this case. So now you need to look at also the constraint MPC as an optimization problem. So now if you see that from this slide I presented today, so you notice that MPC problem is you need to minimize J. You need to minimize cost function J is a quadratic function. You need to have some constraint G delta U less than 0. So G delta U, so here we have a linear constraint, okay? So quadratic function, linear constraint. Why? Because this. So this constraint is a linear, you see? So now you need to solve it. So we need to solve a constant optimization problem, and this is a convex optimization. You need to look at the linear constraint and include the constraint on the input, output, also rate of change, and so on. So how about the nonlinear constraint? So this also could be possible. So now if you want to do the research on MPC, so maybe you need to look at the nonlinear constraint, for example, here. So what is the problem? The problem is a computation. So in Italy, I have a project about the nonlinear MPC. It means that we have a lot of nonlinear constraint MPC. So if you are interested to do some research on nonlinear MPC, so maybe you can contact me, because my students, I have one postdoc, and he's working on the developing the code for the nonlinear MPC. And but we have also used the machine learning, like the reinforcement learning. So reinforcement learning, how it can be used for the nonlinear MPC, MPC with a nonlinear constraint. So if you are interested and if you are doing some research in this area, you can contact me. So now you can see that the MPC has some benefits. So the MPC is easy way of dealing with the constraint and control state. So it means that practically MPC is very useful, because you can consider all the constraint on the state, on the measurement, on the control. So you can get a high performance control very accurate, because MPC you can has a lot of real-time computation, and that therefore is very you can get a very good accurate result. So no need to generate solutions for the whole time horizon. So you need to look at only the next time, and that's it. The next time is only the concern. So the MPC is very flexible. You can do any model, any objective, but these are some pros. But what are the cons and the drawbacks? So the main disadvantage is the online computation real time because this MPC has a lot of computation complexities, and the online implementation is a challenge. How to solve the constraint MPC? So I told you that I talked about the linear constraint, but in the reality, maybe you need to work with a nonlinear constraint. This is a challenging topic. So maybe you will start with the unfeasible solution because your optimization should be feasible, and therefore, if you got maybe you get some unfeasible solution. So robustness, stability of MPC is always challenging topic. You need also to pay attention. So if you're interested, I didn't discuss with explicit MPC, but solving MPC in the online might be a problem. So, but it should be in less than 1 millisecond in the sampling time. So because this is a implicit MPC, so it should be done very quickly. So the solution for this problem, if you want to avoid any the time computation time in MPC, you can come to the explicit MPC or eMPC. But explicit MPC is an offline problem. It means that you need to solve the problem in the offline. So the basic idea for explicit MPC is the offline computation to determine all operating regions. So this means that you need to do a very intensive offline computation to determine all the operating regions. So extended explicit MPC, eMPC controller require the fewer runtime computation. So now eMPC is much faster than the implicit MPC. Again, so to implement explicit MPC, you need to design a traditional MPC, and then because explicit MPC is very similar to traditional MPC, and then you can do some offline calculation for all the operating points. And this controller, you can use it to generate an eMPC for real-time control. So if you are interested, you can also look at this MathWorks information, so more about the explicit MPC. So there are several good references basically for eMPC, for MPC. So if you are interested to learn more, so you can look at this material basically about the eMPC. Okay, so now the first part of lecture today. So I try to introduce you to the MPC. So I told the MPC the big challenge is the task of implementation. If you want to do the traditional MPC as a basic implicit MPC, there is a lot of issues about the computation because they are dealing with the constraint with the larger scale model, and therefore they bring the challenge in the computation. So if you move on to the explicit MPC, eMPC, but the challenge is that how to do all the computation in the offline for all the operating point, and then you need to implement it in the real time. So now the MPC is very practically very useful, but you need to learn how to do some design. As I told you that in Italy, I'm now working on the nonlinear MPC. There is one toolbox has been developed in Italy. If you are interested to look at this toolbox, is open source, and then you can download it from the GitHub. And if you download from the GitHub, you can start to do some MPC design. Of course, you can also use the MPC toolbox in MATLAB, but the toolbox I'm presenting is a bit more powerful for explicit MPC for eMPC. But it depends on your project, what do you want to do, and then there could be some, always there could be some solution. Okay, so now the MPC, I think there is a lot of development. So I told you that now I'm working on the machine learning, how to add the machine learning to MPC. And therefore, if you are interested in some new areas about the reinforcement learning or the learning-based MPC, so the reason is that the MPC, so today I talked about the constraint on the state, measurement, control. But what about the obstacles? Because if the robot or the vehicle goes to one environment is totally unknown. If you want to avoid any collision, how to look at the unknown environment? So then you need to have a learning on your MPC. And that's it. The learning-based MPC is also a very challenging topic. It becomes more and more important. But for the learning-based MPC, you need to know two things. First, you need to know about MPC, explicit MPC, traditional MPC, MPC with the constraint, for the linear MPC, even nonlinear MPC. And then if you move to the learning-based MPC, then you can extend your control result basically based on the learning strategy. You can develop more efficient control strategy to work in the unknown environment. So these are the basically very useful in many applications, specifically for the autonomous cars. Autonomous cars, the system should have an MPC. The car should have a maybe the nonlinear MPC. The car should have the explicit MPC because you need to implement the MPC in the real time. And also, the car works in the unknown environment. You need to know about the learning-based MPC. So now you see that you can go step by step. But step number one is understanding the traditional MPC. And this was the purpose of the lecture today. Okay, so we can have it maybe 5 minutes break. And then if you have no question, if no question, we can have a 5 minutes break. And after break, I can discuss about another part of the lecture today. Okay, thank you. So welcome back to the session. So if there is no question, so I can start to talk about the second part of the lecture today. So the second part of lecture today is about the AI, machine learning, and also involvement in the cyber security. So that's it for today. First, I would like to talk about this AI, machine learning, some assistive cyber resilience. So in this, during the course of this week, we talked about the cyber physical system, we talked about the cyber attack, we talked about the cyber security, cyber resilience, I want to discuss today, and why we should add some AI or the machine learning and what could be the benefits out of it. So these are some the emerging technologies that's it day by day. So these technologies changing, and therefore it's very important always to know how that what is the trend of the technology in this context. So there is a sort of definition of about the cyber security or the cyber resilience. So it says that the cyber resilience so refer to an entity, ability, entity. Okay, so it depends to the cyber resilience. So it refers to an entity ability to continuously deliver the intended outcome despite the cyber attacks. So when we talked about yesterday about the cyber attacks, because the cyber attacks it could be sort of the outliers. So basically in your measurement, so basically in your data. So now you can see that this, in spite of this kind of the cyber attack as a measurement outliers, so the output of the system or the outcome so should be remains stable. It means I should be continuing so in the same manner, so without any abrupt change. So if you want to get such a robustness in the outcome, in the output, in the face of the cyber attacks, so you need to understand how to deal with these kind of the attacks or the major outlet. So yesterday we discussed about some sort of estimation. So you remember that I showed you some sort of estimation design. So, but anyway, so this topic is a very intensive topic because the attacks are changing. There are different type of attacks, and always that we need to be aware of this issue. So if you want to increase the level of the awareness of the system, so you need to implement look at the cyber worthiness. So the cyber worthiness is a sort of assessment of the resilience of the system from the cyber attack. So you need to have a sort of assessment or the sort of evaluation respect to the resilience, so about the robustness, so how much the system is robust against the cyber attack. So these are some sort of the discussion exists in the cyber resilience context. So that's it in the cyber resilience, cyber security, cyber worthiness. And this is also another keyword that basically we need to remember that it also refers to the assessment of the resilience. So the cyber resilience techniques, so there are several techniques. So you can look at, for example, the adaptive response. So if you are doing some adaptive response methodology, so the purpose is to optimize the ability to respond in a timely and appropriate manner. So the second approach, it could be analytic monitoring. So the monitoring means you need to monitor and detect adverse action and also condition in a timely and actionable manner. So if you want to do the monitoring and detection, so this is basically we talked about the health monitoring. So you remember that you need to basically, you need to look at it very carefully. So another technique could be coordinated protection plan. So you need to implement a defense in-depth strategy. So defense in-depth strategy, so this is sort of the coordinated protection plan. So if you implement the defense in-depth strategy, so such that adversaries have to overcome multiple obstacles. So another, it could be about the deception. The deception is a misleading confusion, the hiding critical assets from or expose covertly exchange the asset to the adversary. So this is also another technique we have in the cyber resilience about the diversity. So how to use the heterogeneity to minimize the common mode failures. So in the case of the attacks exploiting common vulnerability of the system operation. So basically, these are some different techniques that we have basically in the cyber resilience. So another technique could be the dynamic positioning. So how to increase the ability to rapidly recover from the non-adversarial incident by distributing and diversifying the network distribution. So dynamic representation, so it's keeping the representation of the network current and also enhancing the understanding of the dependency among the cyber and the non-cyber resources. So this is sort of revealing the pattern or trends in adversary behavior. So another technique would be the non-persistence, about generating and retaining resources as needed for a limited time, reducing exposure to corruption, modification, and also compromising. So privilege restriction, it means restricting the privilege based on the attribute of the user and the system elements, and also realignment, how to minimize the connection between the mission critical and the non-critical services. And also redundancy, it's providing the multiple protected instances of critical resources. So now you see that in the context of the cyber resilience techniques, so there are a lot of techniques. So, but it depends on application. They have what kind of the system to be protected, and then you need to look at. And that's it. This topic is quite expand intensive areas, and then we need to understand many the information how to deal with the in principle with the data and also the system protection. Okay, so in fact, the cyber resilience, so it has a lot of applications. So you see that, you need to look at the cyber resilience in the tools, so in the strategies, in the frameworks, and also there's some advancement and also applications. So now you see that the cyber resilience, it's has opened because of its importance, has a lot of research gaps. So there is a lot of research gaps in the basically in the cyber resilience. But you need to know that what is your interest and what is your competence, how to look at, for example, this kind of problem. So for this reason, the cyber resilience, so of course it has the application, the transportation, to the supply chain, to communication network, to the power grid, and also the health and also the finance. So now you can see that the cyber resilience, so more or less is used everywhere, but the important is to follow some fundamental foundation of this methodology for one particular application is in your focus. So why machine learning? Why we need to use machine learning in this cyber resilience? Because we are wishing to solve a problem, okay? So because we want to solve a problem, and this means that they're not amenable to treatment via a fixed human written program. Because machine learning has a high ability to extract some features, some information, basically, and this should be totally out of the scope of the solving by the human. So in the machine learning application, there could be some sort of problem. So the problem could be the regression, how to look at the predicted value, how to look at the predicted features, and how to look at the classification, because usually you are using the machine learning either for regression, for classification, but in total, you need to look at the trust. You need to look at the trustworthiness. So basically, this is a big challenge. This is a big challenge we have in the machine learning. So the trustworthiness. And that's it for the increasing the trustworthiness. If you want to increase it, so basically we need to look at some explainable AI, and that's it. So the topic of the explainable AI, so or we call it the XAI. So this becomes also important
हाँ जो
in
था वही
terms of
करूँगा
the basically
तो 5 क्वेश्चन भी चेंज कर दिया ना
to understand more about the solution of the problem is under the focus. So there is many problems. So as I told you that the cyber resilience has many applications. So now the point is that how AI model learn about the learning, understanding, and is a normal and also what is the abnormal behavior. So this means that you need to understand about the XAI, okay? So this means the AI. So this means AI. It's like AI, and this means XAI about understanding. So now, if you are interested, you can contact me because XAI. So this is one of the research topics we are working at the Polytechnic of Milan, and we have developed many post-hoc visualization techniques. So you need to develop some sort of a post-hoc sort of a visualization technique. So if you want to do some research on the XAI to understand the AI result, to how the system can understand the normal or the abnormal behavior, we need to look at XAI. So for the post-hoc visualization, you can look at the CAN, for example. So the CAN, for example, the CAN is one techniques basically for the post-hoc visualization. And also you can also use a score can. These are some typical basically techniques we are using. So also you can use the grad can. So there are a lot of techniques in the literature. So basically for the XAI. So XAI becomes a very important topic, specifically when you work with the resilience, because you need to understand this work is very important. So the reason is that when you are using the AI, so AI or the machine learning, so AI or the machine learning, so we call it as a black box, okay? So this is a black box. So when you give the input, for example, and then when you look at the output, so this AI, this model is a black box, black, okay. Okay, so it's a sort of a black box. So in this case, if you want to understand, so what is the inside of this black box? So you need to understand how the AI and the machine learning model has been produced. Because when you have the abnormal behavior, so abnormal, it means that the system has maybe the attacks, okay? So the system has an attack. So if you want to detect this kind of the attack from your measured data, based on the AI and the machine learning, there could be some other issues. Maybe you have a sort of maybe the noise, okay? Maybe the noise, okay? And therefore, it's very difficult. It's very difficult to discuss, to make a decision. So about what is the attack and what is the noise. So now if you want to distinguish, okay, if you want to distinguish between the attack and also noise. So these two topics are basically, you need to develop the XAI. So now the XAI, so it try to help you to understand this behavior. So again, if you are interested, you are welcome to contact me because we have no time to discuss about everything in this course, but it depends on your interest. So I just want to tell you that AI machine learning is developing very fast, and everyone wants to develop different machine learning tools. But important for us is to understand how this machine learning works in terms of detecting the normal or the abnormal behavior. And therefore, you need to understand basically the some sort of a post-hoc visualization techniques. So as I told you that the count, a score count, a grad count, and one of my students, he developed a smooth set. So he developed a smooth a score count, and that's it. We developed SS okay? SS-scan is another visualization, and we also show that it has a very high ability to get a better understanding about the machine learning tools or the deep learning tools. But anyway, so this is about some information about the development of the XAI, specifically for the resilience, security, or the cyber security. So, but when it comes to the research methodology, so the basically for the AI-driven cybersecurity for based on AI or the machine learning for the cybersecurity, so there could be many issues. First, you can develop a machine learning basically tools. You can develop the different techniques for the machine learning. And for the machine learning, you can do some representation learning application because you need to provide some data basically for the machine learning. So but for the representation, you need to get some data collection, some data, and then you can also use it for the machine learning for the training, for example. And this means that we need to look at this data and also representation, and these are the based and then to develop or to customize the machine learning tools. So if you want to get the data, so basically you can also use it some AI-driven techniques or some model security problem. But anyway, the data is important part. But another issue we have about the cyber threat analysis. This analysis, it means that to get some understanding about the threat, what kind of the cyber threat exists. And maybe you can develop some sort of a model, and this kind of a model could be some sort of a statistic model, just to get develop the model to get the data, for example, because you need to come to the data. So now you see that in the research in the case of the machine learning for the cyber resilience, so more or less important part is the data collection because the data, and if you get the basically do the representation of the data, then you can basically develop your machine learning tools. But again, so if you develop a machine learning tools, you also need to develop basically the XAI because you need to exactly to explain, you need to understand how this has been developed. So this topic could be a new topic. Basically, you can add it to this block. So there are many cases you can use the AI-driven cybersecurity. So for example, you can use it for the data vulnerable code analysis, machine learning-based malware detection, insider attack prediction, adversarial machine learning, security incident prediction, intelligent network monitoring. It means that the AI-driven cybersecurity, so it's a very fast developing area and depends on the problem of on the focus, depends on the data acquisition, depends on the data representation, and then depends on the development of the machine learning tools. Okay, so but if you look at some sort of development for the adverse and machine learning for cyber attacks, of course, there's one topic is the car, and also could be related to the some flight vehicles. So it means that there's some advancements of the unexplored territory of adverse machine learning defenses. So we focus on the network security. So you can look at some randomized projection, reducing the course of the dimensionality and benefit that benefits attackers. So, and another could be using some game theoretic formulation that set the limit points of the cat and mouse attack and defense. So it means that there are a lot of advancement for some new areas, how to use some adversarial machine learning. So for this part of application, it also becomes a very hot topic. So I think that there are many projects. If you are interested, I think you can do some good research in these areas. So another issue is about detecting the software vulnerability, because the software, it means the code that basically is always under the focus of the attacks. So I told you that in the autonomous car, so there is a lot of codes written for this autonomous driving. So let's assume that there could be some attacks to this software part. So now the question is that how the AI that uses the machine learning and other techniques so can differentiate the bindings or harmful binary or source codes. So now you see that if we want to look at some changes in the binary or the source code and how to look at detecting some software vulnerability is a very difficult task. So now you see that the software vulnerability can critically to undermine the security of the computer system, so endanger the IT infrastructure of the organizations. It means that if you have a high impact vulnerability, it looks like the bombing. It means it's a very dangerous issue. But the problem is that how to secure, how to detect, and this is basically the challenge topic we have. So now the challenge for the software part, if you have a vulnerability, are difficult to detect, but because of the tedious and the time consuming. So because you need to have we have a sufficient understanding of the projects and the knowledge of the security required. You need to have expert knowledge, but this expert knowledge is always maybe difficult basically to obtain it in basically in different application. So about the security consideration are not prioritized and well organized. So nowadays in many businesses, so maybe the security is not become a very high priority because the people cannot is not well recognized. You see, so in fact, if you have the software engineering, including the program analysis, software testing, and if you have the issue about the cyber security, so one overlap is the code analytics for cyber security. And that's it for this part. If you want to enhance this cyber resilience, so you can use machine learning, you can use the data mining, so you can use, for example, AI. So now this topic is a very challenging areas, and I know that there are many research group in different universities, especially in India. I know that in India there are some universities they are working very effectively on the topic of the machine learning, data mining for the some sort of cyber resilience in terms of the vulnerability in the software part. But these are the very developing topics. But in fact, if we look at it from the data, so if we start with the data, so some data is a labeling data, or maybe you have a sort of you have some unlabeled data. So of course, maybe you also have some unlabeled data. So for the unlabeled data, but if you have a data with the labels, and then you can use it for the cyber security because you can extract the feature. You can extract the features as a feature engineering. So this means that you can use the data mining, machine learning, and then you can extract some features. So this part is a feature extraction. So you can extract. So you can extract the features. And then you can also use the machine learning algorithm. So you can develop the machine learning algorithm, and then you can also come to the evaluation part. Evaluation means the decision. So because you need to make the decision making. Okay. Okay, so this means the cybersecurity. So cybersecurity from the feature engineering or the feature representation. If you represent a feature, if you extract the features, then you can develop the machine learning. So here you can use some supervised learning. You can use the supervised learning, or maybe you can use the semi-supervised learning, or you can use the unsupervised learning. So it means that all the categories of the supervised up to the semi-supervised, unsupervised learning, that you can also developing in this part. But everything depends, this depends on the basically your labor data. But the important thing is that about the data set, because when we talk about the data set, so here you have, again, that there are several problems. One is about the quality. The one issue is about the quality of the data, is about the noise. If your data is how much noise is in the data. So another thing for the data set, so it's about the limited data set. So we have a topic about the limitation of the limited data set. Okay. So this is a very challenging topic. So if you want to use the limited data set, because if you have a limited data set, it means that here you have a limited labels, okay? It means that here you have a limited labels. If you have a limited labels, maybe you cannot use the supervised learning because, for example, in the supervised learning, if you want to use the convolutional neural networks, for example, if you want to use the CNN, okay? The CNN, it means the huge number of labels. The CNN means the labels with the basic the label data should increase. But if you have a sort of a limitation on the labels, you can think about maybe the semi-supervised learning or the unsupervised learning. And this is also one of the research in my group. So in my group in Italy, so we are developing on the machine learning. So what we are doing here, we are developing the machine learning algorithm. So in basically, plus some sort of a limited data set. Okay. So if you are interested, so you can contact me because I try to tell you that what we are doing here. But usually this research is very important because if you have a sort of limitation on the data set, in some particular for the cyber security is a very challenging topic. Okay, So now you can see that if you do some feature engineering, so feature engineering is some sort of a feature representation. If you want to do the feature representation, it means that if you look at your source code, how do we convert the vulnerable code to effective features? So this is very important. It's a sort of a transformation. So you need to do some pre-processing, and this pre-processing is between the source code and then to change it to the features, okay? So the features should be represented. The feature is invariant and also distinctive, and that's it. You can do the classification. So, this area is very important because how to get the features, and because the classification, and later on to look at some sort of the decision making. So this depends on this type of the representation. So maybe you need to use a sort of the deep learning. So if you are using the deep learning tools, of course, you can develop maybe the more features. So you could get some deeper features, okay? But these sort of the deeper features you can get from the deep learning tools. So it depends on your pre-processing data. And that's it. This part is a challenging topic, how to do the pre-processing how to convert basically this vulnerable code to the effective feature. This is a very challenging topic. So another challenging topic is in the pre-processing. So again, the same problem is how to convert the vulnerable code to effective features if you have a binary data, okay? So the previous slide, it was the source code, but if you have a binary data, then you want to get the features and then to do the classification. So again, this is a challenge. So sometimes you can also use the source code, okay? So you can also use the source code, and the source code can be also taken to the pre-process. So now you have a binary data, so you have a source code, and then you can do, and this means that how to make some sort of the feature fusion, and that's it. So here we have the topic of the feature fusion. Okay, so the feature fusion part, so it become important if you have a different source. So the binary data, source code data, how to do the pre-processing. So these are the challenging topics we have in the feature representation. So for this particular code. So now you can imagine that if you want to apply this topic to the machine, to the autonomous cars, how difficult it is because we have a several million source code, and how to detect is a very difficult task. And this is the reason that the topic of the autonomous driving or become very challenging the task. Okay, so the machine learning, as we discussed, is the start with the data with labels, feature engineering, machine learning algorithm, evaluation. So these are the research trends, and therefore, so you can develop different learning, super vector machine, transfer learning, deep learning. So you can develop a semi-supervised, a supervised, or different. So these are the all are the basic research. These are the research trends, and as I told you that this is what we are doing in Italy. So in my group in Politecnico Milan. So I'm working on the transfer learning and the deep learning. So if you are interested, so you can contact me because we are using this kind of development of the machine learning tools for some sort of the application in mechanics. But of course, it's a very hot topic. Okay, so now I'm talking about the cyber resilience for the autonomous car. Okay, so one of the very important application of this topic is about the cyber resilience for the autonomous cars, and that's it. I try to a little bit discuss it now. In this context, basically we can say that the attacks category for autonomous cars, there are different attacks. So from the automotive, basically on the automotive control system, on the ECU, on the in-vehicle network, on the automotive key. So we have attacks on the autonomous driving system component, like a sensor or the mobile application APP. So we have attacks on the V2X, on the vehicle to environment communication, or there may be some other, the VANET is a vehicle ad hoc network. So VANET is a vehicle ad hoc networks. So the attacks on the VANET and also infotainment attack, we need to do some sort of the risk assessment and also analysis. So including the risk assessment, attack tree, and also some other. So now you see that the categories of the attack research on autonomous vehicles, there are different areas. So from the control side to the components of communication and also to the assessment. So all should be considered. So the defense category, the category of the defense for the autonomous vehicles, if you want to look at the defense category, so you need to look at the security architecture for autonomous defense. So you can look at the CAN issue security, environmental security, security design, the process, and framework. So you can also look at the defense category in terms of the intrusion detection system. So for example, you can look at the IDS, intrusion detection system is IDS. So you can look at the IDS for CAN, IDS for the VANET is a vehicle ad hoc networks. So you can use the AI and the big data, AI with the big data, machine learning, deep learning, cloud, big data. So now you see that the defense category goes from the security architectures to the detection mechanism and also using again the AI. And you see that the AI and the machine learning is always exists also in the defense category and also in the category of the attack assessment. So always AI is involved. So this is about the cyber component in an autonomous basically the vehicles. So as we see in this slide, so the system has many sensors and with a different coverage. So you have some sort of a front sensor, so the rear sensor, and also the side sensors, and each sensor has a different coverage, and it means that the potentially this machine, because of the many sensors, as we discussed also yesterday about the ultrasound, a short mid-range radar sensor, camera, LiDAR. So potentially there could be high attacks on this machine. And therefore, we need to look at how to make it secure. And this is a reason that the cyber security for this application is very important. So how we can secure our connected system? Connected system is another thing. So assume that there are two cars, for example, there are two cars, so on the road. So if these two cars, so maybe they want to be connected, okay? So there could be some sort of the communication. There's sort of the communication between the two cars, number one and also number two. So this system is a connected system, and for this connected system, so this connectivity comes with a risk, okay? So if you have a connection, so always the risk exists. If you want to do the protection of a smart component and devices from the time they are manufactured until the end of their life cycle. So now you can see that this system has a smart sensor. So now there is a lot of a smart sensor, and therefore, if you want to secure it, you need to protect it. And that's it. These are the some challenge we have about the security for the connected cars. So connected vehicle threats. So if you look at the threats, So especially for these cars, as we see that from the manufacturing, so when they are manufacturing the cars, and also for the mounting this smart sensor or smart infrastructures, so because their car has a connection to infrastructure, and also the car has some smart sensors. So now you see that the electrical component, a communication channel, and also some multiple interface between the vehicle and external, and also some sort of data transfer outside of the vehicle, which could include the data transfer to the cloud, so the data to the cloud. So now you see that in all of these items, so you have a threats. And that's it, how to secure this connected system, including this kind of the connected vehicle threads. So it's a very challenging topic, and this means that machine learning could be very good tools to deal with this kind of a big data, with the big data you have in this application. Okay, so if we look at this case, so you remember that I told in one of the lectures about the alternative information security standard and regulation, okay? But this topic is very important, automotive information security standard and regulation. So it starts from 2016. So it's not a very long time ago. It's more or less than 10 years, okay? In less than 10 years, so this standard has been established for the security of the autonomous security of the cars. So then we were from 2017, 2018, so including the EU, European Union, and also China, and also some USA. So you see that there, or the even UK, they have developed many standards basically for this cyber security. But anyway, this is developing. But of course, in all of this development, always the main issue is about the cyber security. You see, it's about the cyber security for these systems. So it means that how to secure it. So these are the very advanced topics. That's it. They are developing very quickly. But important is that we need to understand. So basically, how our competence could be useful, basically to understand and also to use it in our field. Okay, so there's some key vehicle interfaces that could be exploited in the vehicle cyber attacks. So some important parts for the vehicles. So there's something about some sort of the device, like the communication, like the Bluetooth and Wi-Fi or the mobile. So from for example, there's some component like the compact disc players, so or there's some satellite radio, all they could be the one threat for the cybersecurity. So about the keyless entry, so remote keyless entry. So about the onboard diagnostic board. So you see that there could be some direct access, short-range wireless, and also the long-range wireless. So in fact, this could be one sort of the vehicle key vehicle interfaces. So we should also consider. So in this case, the cyber attacks for the car, so basically the becomes for the long range wireless. So you see that for the long range wireless, so the attacker can attack to the different component of the cars. So for example, from this the transmission to the mobile or to the radio or the other basically the Bluetooth devices. So there could be some issues related to basically to a steering control unit, a tire pressure monitoring system. They can attack the braking system mechanism. They can attack the telematic system. Even they can attack to the engine control unit. So now you see that there are a lot of potential points to be attacked from outside, and that's it. How to secure these cars. we need to develop different layers based on the standard and regulation to protect so this kind of the application. So we have a layer approach. A layer approach to enhance the autonomous vehicle cyber resilience. So it means that if the attacker want to attack the system, so there are different layers. So we have one layer about the infotainment and the other system layers. We have one layer as a firewall and the gateway and also intrusion detection system IDS. So you can develop the IDS for the intrusion prevention system, or you can detect anomaly message and also so on. So we have also one layer for the safety critical system for the braking, engine, and steering system. So even they can also send some message encryption and also authentication. So the authentication, it allows to secure communication between the two devices. Okay, so you can secure it at the different layers. So you can secure it from the authentication between the devices. You can do some safety critical system. You can develop IDS and others. So you see that there are different layer approach to enhance this cyber resilience. So for the vehicle cloud, because vehicle cloud collaboration is a very hot topic. So for the autonomous driving, but even if you want to add it, this vehicle cloud collaboration plus IDS for the intrusion dynamic system, for example, if you want to develop it. So in this case, so you can see that the different vehicles extract multi-dimensional features and upload them as the order of the generation. So the cloud server, so you can see that the data from the connected cars, so this data can be collected in the cloud. This you have a cloud server. So in this case, so after collecting of the feature extractions, so from all the vehicle based on the data from the vehicle, such as the battery, voltage, and the many different data for each cars. So these data can be transmitted. It can be transmitted basically to the cloud. So in the cloud, you will have some model training based on the feature extractions. You see that you have based on the feature label, you can do some pre-processing. So you can do some pre-process and then to get the different features, okay? So when you get the different features of the prediction, so you can apply to the different vehicles, and that's it. You can apply some sort of the security tools to the basic to the system to secure them. So based on this data, they can develop some attack detection mechanism, and then they can even detect the source, or even they can trace the source of the attack. So this mechanism basically now is applied in the autonomous cars, even for the connected cars. And this is a very challenging topic, and it means that if an attack is detected, the vehicle compares the accumulated clock offset of current message with the IDs and the ID to ECU in order to track basically the source of attack. So this mechanism usually is a topic of the vehicle cloud collaboration. So in terms of enhancing the security of the cars. So for the connected cars, assume that there are two cars like this, they are driving on the road, and then there could be some cyber attacks, okay? So if you look at this, so these two cars, they have a sensor, like a radar sensor. Radar sensor always, they check the distance between the two cars. So if the radar is become negative, means that there should be some braking. If not, is no action. So now you see that for the autonomous driving, the radar sensor, they always check the distance between the two cars. But this is a no attack. You see, here there is no attack. But the problem is that if the attack is appeared, and then if this become a wrong information, and if this become wrong information, this is very dangerous. And then we need to pay attention how to secure the sensor, because this sensor should not be affected by the attackers. Okay, so now you see that here there is the three different actions. So here we have this one is similar the demonstration part. So here there is a control based on the radar sensor, and then you see that the car stop at this without hitting the bomb. But if there is a manipulation on the sensor data, so you see there is some sort of the attack. You see, so here there is a sort of the attack, and they are changing of the basically the sensor data. So now you see that there is a sort of the collision with this bomb. And even this amount of the radar sensor increase to +2, then this also another attacks. Then you can see that there is an accident. So now you can imagine that for the autonomous cars, and if the radar sensor becomes under less security, so now how dangerous is this application? So now I can show you that in this particular case, I think here should be one video. I want to show you just a moment here. Okay, I want to show you the one video, so just a moment. I think okay. So now there is a video. You can see how the braking system works. You see. So here the car is coming to this bomb, but there is no attacks. But here is a second part. If there is some manipulation on the radar sensor, and then you see there is an accident. You see. So now it means that if the information from the radar sensors, so if it becomes wrong information, so based on the attacks or now you can imagine that how the cyber resilience that will become very important. So if the system is secure, or the attacks or the becomes in the role of the changing the radar sensors, and this becomes a very dangerous issues. And this is the reason that nowadays there is a lot of research how to enhance it, and that's it in Polytechnic Milan. So if you are interested, we have a very good laboratory. So as a for the vehicle lab demonstrators, and we are also doing a lot of experimental tests for these applications. Okay, so at the end, development process for the vehicle safety system, as you see that there could be basically the many development like the V mode. So the V mode is this shape. So it's for the systematic safety and also the security design. Yes, Dr. Kuha, do you have any question?
Yeah, sir, actually, I just request you to kindly give us 5 minutes time for the interaction, sir, as I requested you before.
Okay, I think,
so
yes, you're right. This is my last slide. I think
okay,
just
sir.
for your
Sure.
information that, yes, you're right. The vehicle safety system, they should follow the V shape. So as we see that about the security implementation, about the software implementation to the hardware design, hardware layout. So there could be a lot of challenging topics. So this means that we cannot discuss about all the aspects, but this means that if you work your project related to the autonomous vehicles, so the vehicle safety, we need at least to follow some standards. And this is the reason that enhancing the security the first priority. I think I can stop in this slide because we can, if you have any question, then I think we can discuss it. Do you have any question or?
Participants, if you have any questions,
Yes, sir. Good afternoon, sir.
Yes.
Yes, sir. Sir, I have a question, sir. So, what are the effective methods, sir, for securing this control loops in networked CPS, sir?
Okay,
So, you
so
have shown that,
it's a good.
yes, sir. You have shown the example of autonomous vehicle. So, we are also working in the autonomous vehicle, and the next stage of autonomous vehicle is connected cars, sir. So, how we can secure the control loops in this networked cyber physical system?
Okay, it's good. I think your question is a good question, and of course, because of time, maybe I cannot give you the more details because the next my slide was about exactly your issues about the connected cars. You see,
Oh, thank you.
so
Thank you,
your
sir.
question is about this point, about the connected cars, right?
Okay.
So like this. So actually,
Yes, sir. Correct.
yes, I think your question is about this, right?
Yes, sir. Yes, sir. You are exactly
Okay,
right, sir.
so exactly. So because of time, I didn't we have time to go, but I can send you all the PPT. So the main challenge for the connected and autonomous cars, you see this technology from the steering, accelerating, the deceleration. So about the connected car technology for communication to each other, and it means that we have also developed some sort of technology for the communication between the cars. It means the vehicle connectivity, vehicle automation, and if you want to reach to CAV. So of course, maybe you work on the AV, automated vehicles, but the CAV is very important about the connected and automated vehicles. So for this particular case, so we have also developed different tools. So about for the vehicle communications and also to some challenges we have in this aspect. So well, I can tell you that several of my students that they did a lot of project for this intersection for intersection. So if the cars want to pass through intersection, you see there are 4 lines. And in this case, so we have developed a lot of algorithms. So based on MPC, for example, or other cases. So try to basically to avoid any collision. But of course, in no time, I'll show you all the results, but you can contact me. So, but anyway, this is my students, you see. So he has also he's working for the connected cars, and we have developed many techniques basically for this part. In fact, this is a very challenging topic, and also we have also recently worked on the HEV. So for the H hybrid electrical vehicles, and we have a lot of the solution basically for this part. So for the energy management (EMS), for the HEV, and also for the plug-in HEV (PHEV). So, very briefly, that we have tried to apply many learning tools like machine learning. We have used MPC. So for the different scenarios, so we have the, but for your question, because your question is exactly related to what we are doing, so you can contact me and then we can discuss it later. Okay.
Sure, sir. Thank you, sir.
Mhm.
Sir, one more question, sir.
Yes.
Sir, actually, how we can effectively co-design the communication, computing, and control in a cyber physical system, sir. So, how we can effectively co-design the three different domains: communication, computing, and control for cyber physical systems.
Yes. Actually, I can explain you from this picture. So basically for the cars, I can come back to this slide. Yes, this slide, okay? So this slide, you can see that if you want to effectively look at your integration of the networks and also the, but usually for the vehicle, because we work on the AV autonomous vehicles, usually the cloud is a one challenge issue for us. So this kind of the cloud information, how the information in the cloud can be processed. So you need to look at the model training. It means that you need to see how the features can be extracted or how the feature can be predicted. So based on the feature extraction, feature prediction, so of course, this is your data because these are your data from the cars. So usually for your question, so if you have a good training model you can develop in the cloud servers, and this can give some sort of information, so basically to the cars. So now you see that based on that, we can also look at the attack detection and the source tracing. So for your question, I can refer you to the part 3 and the part 5. So you can look at the model training for the feature extraction, and then based on that, you can develop some mechanism for the detection part. But of course, these two parts is the answer to your question.
Okay, sir. Okay, sir. Thank you. Thank you very much, sir. Thank you, sir. Excellent
Okay,
interaction with
thank
this.
you. Thank you.
Thank you. Thank you, sir.
Are you from university or from company, sir?
Sir, actually, I am from SRM University, Chennai.
Okay, okay.
Sir,
If
we
you
are
can,
yes, sir. Our main domain is networked microgrid and cyber physical power systems, sir.
okay, good.
So in that,
Yes,
the main there are a lot of issues in a resilient control in a networked microgrid as well as in cyber physical power system. Currently, we are working in a hydrogen powered autonomous vehicles, sir.
okay, very interesting. So you can send me an email because the hydrogen-based, hydrogen-driven cars is also our research focus in Italy.
Yes, sir.
So
Yes, sir.
you can contact me and then we can discuss.
Sure, sir. Thank you. Thank you, sir. Thank you. Thank you, sir. Thank you, Deepan, sir. Thank you, sir.
Thank you.
Thank you.
Thank you. Sir, if you allow, then we can have a quick interactions with the faculties from our department and the faculties, those who have participated in this course outside of MNNIT.
Okay.
Uh,
So
Thank
I
you,
can
sir.
stop my I can stop my sharing, right? Okay.
So it's fine, no issue. Okay. May I request the faculty participants now you can turn on your mic and you can have an interactions with sir. Dr. Saringi.
Yes,
Yeah.
good afternoon, sir. So myself, Dr. Soumendra Sarangi. Particularly, I'm working in a power system protection area. However, I'm also interested in applying the cyber physical system for the relay. So my research is in preliminary stage. However, I want to just get some insight from your side that if you're having a bigger power system that relay malapersonation because of this cyber attack, is it possible that we'll be having a blackout in our power grid?
Yes, thank you for your introduction. Yes, exactly. So for the power grid and also for the resilience of the smart grid or the power grid, because of the scale of the system is relatively large, we have a distributed system on the larger scale. At the same time, we have also some challenge with the data because you have a lot of from macro grid. If you're going from the macro grid to the smart grid, so they basically from the sensor, from the system operation, the information. So the big challenge is about the data, but of course, cyber security, cyber resilience is also very important. Basically, it has an important role to enhance the protection level of the system. Because I work on the wind turbine for many years, and that's it. I'm familiar with the grid side for the offshore wind. And I can tell you that the protection of the IDS for the intrusion detection system for the IDS for the wind energy. So nowadays it's a very the ongoing research areas in Europe, of course, in India should be the same. But in fact, you need to develop some features can be extracted from your data. So if you have a large data, because for the wind turbine, we have every 10 minutes some SCADA data. SCADA data can be monitored. Maybe I can show you one a slide because this mechanism is what we are working on the wind energy. I can show you one slide. And here you can see that how to look at the monitoring of the this phase. So I can start starting my lectures. Because we work on the health monitoring of the wind turbine, but I'm not sure if you are interested. I can also show you a little bit more details about the health monitoring system and also related to the detection of the fault or even for the security of these large platforms. So in this area, what we work, I can show you in this just a moment. I can explain okay, so, okay, I can share my screen. So, okay, so